Good morning, everyone. There's a raining day. Good weather for sleeping. Hope you all are ready for the class. Any questions from last week? Lecture or tomorrow? Any question you want to raise that can discuss? I encourage you all to ask questions during the class. Any questions? Any questions? In the last yesterday class, they asked me to show the question here. So last week we did we are given this two condition here, and we are asked to prove this. Okay. I think there's one technical step here, which I think I did something wrong. The other, just normal instantiation law, De Morgan's law, prediction, and so on. But one thing to take note here is about this Q or not P and Q or P. Okay, this is the distributivity law. Yeah. Okay, and you'll realize that after you apply the distributivity law, you get a contradiction. And then you use the identity law to remove the contradiction. And then you will get what you want. I will update the note. Huh? Yeah. Screen is black. Screen is black. Yeah, why the screen is black? The screen is black. Yesterday also like this. Okay, let me restart it. Yesterday also got this problem. Nothing. Okay, doctor. Okay, just one point I want to point out is this technical part here. Okay. I'll update the knob afterwards. Any other question? Any other questions? Any other question? Just don't be shy. Don't be shy to ask questions. Okay, when I go fast, please lock me down. Okay, if not, then we go to this week material. So this week we'll go keep continuing with set theory. So last time we stopped at the subset concept. So how to show two sets are equal? You have to show that one is the subset of the other. Okay. For example, if you want to show the set A and B are the same, you need to show that A is a subset of B and B is a subset of A. Okay. And you need to recall what's the definition of a subset. But now I recall the definition of proper subset, which is really the subset, but they are not equal. So here, at the same time, I recall what is subset. So for every x in A, x has to be in B. Okay? And if they are not equal, you can find something in B which is not in A. Okay? Remember that I showed this example here. Okay? And then I draw out how they sit between each other. In the last class, also some people asked me about this line here. So this is just an idea to show you that the R can sit differently inside another set. Whether why these R are equivalent, it's not in the scope of this class. So I just giving you an idea they can sit differently inside the set. Okay. Okay. No question? This one I think we talked about it last time. Okay. So let's see. Okay, so today we will first talk about how big or how small is a set is. So this is the cardinality of the set. Let's define. Let's given a set. Okay, let's be a set. The cardinality. So the cardinality of a set A is the number of distinct elements in X. Okay. So if okay, let me denote by modulo of X. Okay. If X equals to n for some n in n, okay, then not then X is finite. Okay. Otherwise, the set X is full. Okay. For example, let's recall the set, the clock number was like 1, 2, 3, up to 2. So what's the cardinality of C? Hmm? 12? Yeah. Okay. So there are 12 distinct elements inside X. Okay. How about the cardinality of the empty set? No, 0. Because there is no element inside the empty set. Okay. So C and empty set are finite set. Okay. But for example, N, Z, R, and C. Okay. Okay. And then another Q. R. Okay. Yeah. Actually, inside infinite, they still have order. So this one is just some extra, but I think won't cover in this course yet. So this one and the same thing. This one is larger. Just for your information. Okay, next. So we only learn finite set, infinite set. Okay, next we learn the power set. So given a set, we can study all the subset inside. So the power set of all subset, sorry, the power set of X is the set of all subsets of X. So what is a power set? Power set is another set. And then what's the element inside the set? Is all the subset. Okay. So we will denote by px. Px. Okay. For example, let's look at this set here. 0, 1, containing 0, 1, 2. And this is our set. And last time we showed that every set have two subset, right? One is empty set, one is itself. Okay. So that means here must contain an empty set and itself. Okay, what are the other subset here? For example, 0, the set containing 0. So the set containing 0 is a subset of 0, 1, 2, 0, 1, 2. So that means what? For every element here, it is an element here. Okay. So 0 in here, 0 is in here. Okay. Similarly, we will have 1, set containing 1, set containing 2. Any else? Set containing 1, 2, 0, 1, and then 0, 2. Okay, I think that's all. Yeah, all set. Okay. Okay, next. Next, so we study the set itself. We also want to study operation between two sets. So now we want to introduce product of two sets. Right. So before introducing the product of two sets, we need to introduce a new terminology first. So this is an ordered n tuple. Actually, this one is familiar to you, like the xy coordinate, but I introduce it as a generalization of that. So it's a round bracket A1 to AN. So it's the ordered collection, meaning the order is very important. If you switch the order, it may represent different elements. So you've got A1, A2, up to AN as the first element, second element, and so n tuple. Okay, so from here on to define the products. Oh wait, so this is none, but for example, if n equal to 2, this is the order pair, which is the xy. I mean, xy coordinate is one of the examples. Okay. If it's better for me to make this one. Okay, let's see. Okay, so let's define the products. So the products we are defining is called the Cartesian product. Okay, so so we introduce the Cartesian product. And B. Okay, so Cartesian product of two set denoted by A cross B is still a set. Yeah, it's another set. So what's the element in there? It's all. It's the set of all ordered pairs. Where the first one is in the first coordinate. The second one is in the second coordinate. Okay. So in the formula form, we will write the order pair such that A is in A and B is in B. Okay. So you notice that I wrote the column and then equal sign here. Okay. It's because I'm defining this as the set here. If I wrote equal here, there's something to show. Okay. Equal means equivalent. So remember, just now I said that two sets are equal if they are subset of each other. Okay. So when I wrote define here, it's like the first time this appeared, I define this guy to be this set here. So the definition of this is this set. Yeah. Okay. And then okay, let's see give the example. Okay, example. So let's look at those two sets here. What's the what's the Cartesian product of A cross B? You think? Huh? 1, 2, 3. 1, 2, 3. Why 1, 2, 3? No, just A cross B. So it's just two. Just all the pairs. You got 1, 2, for example. Hmm? 1. You can take one in A, take one in B. So I take one in A, take one in B. Huh? What? 2, 1, 3, and then 2, 3, and then 2, 2. Yeah. Yeah. Take one in A, take one in B. Yeah, discrete. So another example is you take R cross R, for example. Okay. Okay. But in general, so in general, A cross B is not equal to B cross A. Okay. For example, you can figure out this case. So example, not example, exercise. So exercise, find B cross A. Okay. And then show that they are not the same. They're not the same because they don't have the same element. They have different elements. Okay. And then you also can try to generalize this definition to products of set. Here's the product using this ordered and tuple definition here. Okay. Any question? Okay, next. Next, I want to make another description of set formalized. So given a predicate, and this one is linking the predicate logic and set theory. And the domain, so we define the truth set of P to be the set of elements P for which X is true. Then the truth set of X is denoted by such that Qx. Okay, for example, so in this case, I want to stress the importance of writing domain inside your set. So you need to always specify the domain where you are picking the element from. Because if you put different domain, the set will be different. Yeah. So let's see this for different domain, but with the same predicate. Okay, I didn't change the condition. But I changed where I can get the candidate. Okay, let's see what happens. So in natural number, what's the number that take the fourth power equal to what? 1. Anything else? 2. Anything else? No, nothing. Okay, 1. In Z, how about in Z? -1 and 1. Okay, how about in R? 1. Anything else? -1. -1. -1. Okay. -1. Anything else? What? I? I is not in R. I is in here. I. Anything else? -1. 1. Anything else? Hmm? Anything else? -5. Yeah. Okay. That's all. So see, they result in different sets. Again, in particular, let's call this. So A is not equal to B. B is equal to C. C is not equal to D. Okay. So yeah. So this is a degree 4 polynomial, supposed to have 4 roots. So all the 4 roots lies in complex. This is some other theorem. fundamental theorem of algebra. Okay, next. So now we know how to multiply two sets together. So now we want to take union, the union two set. In this concept, maybe exposed before. So take the union of the set. So how do you use the predicate logic to explain the union? The notation for union is cut A, cut B. Okay. So the union of two sets is still a set. It's still a set that contains what's the element in there? So the elements are either in A or in B or in both. So in the set notation, was to write like x such that x is in A or x is in B. Okay. Similarly, you can generalize this to n union of n and n set. I can take the n set. And this is called a finite union. Okay. And you also can take up to infinite set, infinite union. Okay. Have you learned this notation before? Yes. Okay, great. Yeah. Okay, so this is actually get defined. So this is actually this. Okay. This is nothing but the left hand side. This is also nothing but left hand side. Okay. So this is just indexing alphabet. So maybe you also can change it to like J. Okay. Doesn't matter. But when you run this J usually run in integers. So if I put 1 here, n here, meaning like 1, 2, 3. So there's a gap. They want like 1.1, 1.2 like that. So usually this one is, this indexing set is in uh, Z, Z or N. Yeah. See where it starts. Usually Z. Okay. We can start from negative. So example. So let's take the union of 1, 3, 5. So 1, 3, 5 union 1, 2, 3. What do you get? 1, 2, 3, 5. Yes. Okay. So yeah. So one skill you need to master in this course is how to show this set equalities here. Yeah. Maybe I do it once here. So when you write this equal sign here in your mind, you should think of the two set inclusion. Okay, why is this true? So first you need to show one inclusion. Okay. Second, you need to show the other inclusion. Okay, there's two things you need to show that two sets are equal. Two sets are equal. So something like this. Okay. So what's the definition of subset? You need to take every element here and then show that it's in here. Every element here, oh sorry, the other thing. Every element here, it is in here. So let's try an example. So let's take so take x in here. Okay. So that's mean x is either in so by definition x is in here or x is in this side. Right. So if x is in here, it is either 1, 3, or 5. If it is in here, it is either 1, 2, or 3. Right. So a bit tedious, but in general, this is how you show it. If x is in 1, 3, or 5, then x equal to 1, 3, or 5. If x is in 1, 2, 3, then x is equal to 1, 2, or 3. Yeah. But in both cases, uh, hence x is in 2, is in 1. Okay. In both cases, they are all inside the right hand side, the set in the right hand side. Okay. So similarly, you need to show for the other direction. So I keep this as an exercise. Any question on showing this part here? This is quite explicit because the set is a finite set, so you can go through all the elements. Yeah. Any question? Any question? Okay, next about R union N. What do you get? What do you get? R. Okay, so you get R. So how to check? Similarly, you need to check this set inclusion here. So do this set inclusion inside your mind, or write it out. If you are doing it first time, write out why all the element here is in here, all the element here is in here. Okay? This is something you need to master. Okay, next about this. So let us take the union of intervals, those intervals. This close interval. Take a finite close interval of minus I. The second one, we take infinite union of them. Okay, let's spend about 2 minutes to think about these two questions. You can discuss with your friends. What's the finite union of minus I, close interval, and the infinite union? Any idea? What's the finite union of minus I, the closed interval of minus I? Hmm? What's the set? Any idea? Huh? Any idea? Any idea? Huh? Huh? N plus one divided by 2. Why? Why is this? Mm, no? No? You mean this? You mean something like this? No, no. Because n is in here, but n is not in here. Any idea? No? Fall asleep already. For second one is zero number. Wow, you figure out the infinite one, but okay. Easier. Or infinite is easier. Infinity is something like the mathematician always stuck on. How about a finite one? Huh? No idea. So my claim is from this is a closed interval from n to n. Right? So actually you can see from here. So this one actually form a chain. Yeah, this one form a chain. Okay. Yeah, this one form a chain. So yeah, of course when you see this, you need to show the set inclusion. So everything here need to show that it's in here, which is easy because you already contain one copy of it inside here. Okay. So everything here is in here. And for all things here, you need to show that everything is in here. The next one is this R. Maybe this is a bit hard to show because this is infinity, but this case, this is R. Okay. Yep. Huh? Zero is in here. But infinity is not included. No, nothing, no, infinity is not real or integers. It's not real, it's not integer, it's not anything. Okay, it's not real. Infinity is not real. Yeah. Okay. Infinity is not real. Okay. So infinity is not a number. Mm. Okay. Okay. Next. What did I say? Hmm. Okay. Next, let's talk about this intersection. Before we go to break, let's finish this part here. So intersection. Okay, intersections. for the intersection of A and B. A and B. Yeah. So denoted by A. This one is cut. Now it's cat. Cat B is the set. Is another set. Okay. So union is a set. So you take two things, you get another set. You take two things, you get another set. Okay. It's the set containing elements in both A and B. So A intercept B is the element that is in A and in B. Similarly, you can generalize this definition here. So you can generalize to like finite intersection and also infinite intersection. Infinite intersection. Okay, so let's give an example. For example, 1, 3, 5 intersect with 1, 2, 3. Okay, what's the intersection of this set? The set containing 1, 2. Okay, 2. R intersect with N, what do you get? Yeah. So you will see that the cardinality always like reducing. It's reducing. How about this one? So take a series of intervals here. 1 over N. Set. Minus I from minus 1 over I over I minus 1 over I. And then the other one I take the infinite. Okay, so I stop here. Can get rest and then think about these two questions, then we come back. So I stop here. Let you think about it. And take a 10 minutes break and then I'll come back.上周没有来，
对，我上周才
不是已经不用签了吗？
真的吗？
啊，对啊，不是有一个说只要填那个什么来可以？
填啥？不是填这个吗？
这个好像不需要了，不需要，不需要哎。
那我填啥？
我看一下，你没有这个通告吗？我看一下啊，好久之前。
是我上报，因为
我不知道，因为我们是数学组，他们有发，我不知道你们有没有发。哎，这个只要填这个 link 就好，不需要再什么一直签名。你们有没有？你们没有吗？没有吗？哦，那跟你们一样吧。你招也没有用诶，你有 link 吗？
哦，对哦，
对啊对啊，没有那个 link 诶，那个是一个 Microsoft Form link，你们没有吗？
我们没有在 Teams，我们的电脑没有加。
对，
因为这个是数学组的，所以你们应该有你们是 AIT 的，应该有你们的，没有吗？没有任何东西。
对，我们
奇怪
的那个的 group
嗯
从上一个学期结束到现在就没有什么新的。
哦，这是我们的算是秘书诶，不知道。发的。对对对，来，
刚才有一个 I， 不是后面，
前面这边
这里
这里
这个为什么不可以加 I square？
你说 I square 哈，可以加，但是我加给你看是吗？I square 是简易嘛，现在还是简易。对，所以加进去还是
这个 I 四次方
I
，X 对吧？
对对，
还是那个 S 对是那个地方。
I 是
I 是什么？
square root 那个地方。
对，square 对，I 是一个号码，that square 那个
真的？
对，没错，对，Yep，
我刚刚大的那个 union 有三个符号，
这样，
它是我们是看里面的这个是这样，然后不看
没事，
现在这样这里
这里，Yeah，
就比较说第一小题那个
Yeah，
我讲它是最后是负 n 跟 n，我讲负 e 是包含在 n 负 n 里面，然后 e 是包含在 n 里面这样的意思。
不是啊，不是，这个的这个刮胡的 definition 记得吗？是所有的 x 在 real 里面 such that 这个 x 是小于 b 和小于 a，这是 closed with 要包括 a 和 b，是所有在中间的东西。
就负 n 到 n，e 是负 e 小于，
所以是所有号码在减一跟一之间。
所有号码在
你讲这个
对，
所有号码在负一跟减一之间。所以如果你想象你的那条线的话，所以所有在减一跟一里面的号码都在里面，这样子。
哦，它这个是一个 interval，然
对
后这个打开负 n 到 n，所以它就可能
对，呀，
老师
这个不是有的吗？
还给他
对，
它是像反正它是 interval，对，
是哈，OK，对，这样的话，我就给他再提醒
叫老师 send 你咯。
什么？
我们是没有啊，这老师可以帮你签。
签一下哈，OK 啊，签一下就签吧。因为你上个礼拜是那个考 line quiz 的那个，
意思我是补考了呀，我还给你发那个信息。
你是那个 online 的吗？
你还给我把成绩都改了。
把成绩都改了。
对呀。
寄回给你了。OK，我知道了。你是在听你那个发给我。OK。
But can I see the
Yeah.
the latest slide?
Latest slide. This one.
Okay, this is intersection, right?
Yeah, intersection.
Is this using
Oh, sorry. Yeah. This one wrong. Hey, why don't you point out just now? Yeah, this one wrong. Intersection.
可能画的有点小，我都有点看不太清楚。
OK. Yeah, later I will tell them. This one intersection. Okay.
Mm. 所以第三题那个就是负 n 到 n，
哪个？这题？
负 n 到 n，
这一题，这是不一样的题目。
可能 interval 在有点小。然后讲要找 intersection，所以最后一部分是很多共同的 intersection。四题没有一出那个经理的头发，1 divided by 这个我也想不出来。
看一下。
它也是那个符号的。
这是一个。 什么符号？什么符号？你指什么符号？是一个号，是有号码？是有号码？
是有号，
嗯，啊，是有号码。
应该跟1.65。
哎
就我
，OK，之后也会上传，听得懂吗？
听得懂
听得懂。
我上回就是只看这个还是三
啊，我故意不写，然后你
我就自己一个一个，
啊对，
下面有一个地方，
你看你卡了，
对，
你有试过吗？看看。
我看那个我后来就是看不懂，
啊
我才知道。
，OK，好，对，
这个问题出在哪里啊？1.6，我昨天是解到这里，然后我就解不下去了，我就碰什么问题？
哦，没有这个，
这个是这个的，对，这个是给的，然后这个你要做出来，这个是买的两个，这一个是从这个地方，然后这一个是从这个地方这个，因为你有这个，你可以可以多一个，这个是 S 然后这个只是把它。把它那个画反然后它这边跟这边是长一样的，然后这边是反的。只要有一样的，你就可以想那种底模跟不是底模跟
然后我们差不多，就还找两个老师签。
对。
我都退一半了。真的，有点。
哦，因为他们两个的价格很相似，所以哦，就是他跟他是错，所以这个一定是错了，对，错了，对，我们错了这个还有就 get 这边是你现在是错的 get 下来，不是，其实我觉得就是他们是说好的。其实人提的更特，然后这边才能 lost。哦，就到这边就爽哦。因为这个 C 是我要 proof 的，没有，它 C 是任意的 C，instate，对，你又可以退回来，就是因为它是 universal，这个就是任意 C 还是对。写这一个任意 C 是对啊，就可以对付任意的。Simplification 的话是怎么一个意思 ？Simplification，就它也是其中一个版本，这个 Simplification。哪一个？找这可以找出来。那这个是讲就是direct for
哦，这个啊，就是如果你有好的话，你就可以把另外一个推出来。
我就去掉这样子，divide 就是有点像 deduction 这样的，
可以，
addition deduction，
我
一个是加，就是
哦，不可以推出。如果是如果那边是就不可以这样子推。
就不可以。
因为你不知道哪一个会对。
哦，好的话就是要它后面那个是 false，或者是前面那个是 false。
如果其中一个 false 的话，
false 的话
另外一个就要对。
啊，另一个就是直接继承下来。
如果有知道另外一个是 false， 如果知道另外一个是 false，
然后就需要你给分对。
对，
老师考试的话，就是给两个东西，然后叫我们推这种东西。
有可能。
我说你出多一点 induction 那个好做，
哪一个？
这个 induction，来不懂，proof by induction，
哦，proof by induction 啊
这
，OK，
个好做。
不错啊，可以可以可以，应该会出那个，但是我不知道出哪一期，会出一个 induction 的题，
proof 那种 divide by 什么什么的，
因为这一科是我特别放进来的，
那个
目前
都可以 divide by 几
something like that，
啊，那种就好做，divide by integer。
可以可以可以可以。Okay, I think yeah, very good. Someone found out a mistake. So actually this is an intersection, right? This is supposed to be intersection, not union. So this is intersection. Okay. So maybe a bit too small. It's not. Yeah, intersection. Okay. Okay. And then one way to think about just now, this in case you forget the definition of this closed interval, right? So draw out the picture, maybe it's easier. So you got a real line. So the interval of -1 to 1 is here, and then -2 to 2 is here. This is the chain I'm drawing. So if you translate to this picture here, so like this, maybe it's much easier to see in this way. Okay. Okay, so what is the finite intersection of -1/i to 1/i? It could be 1/n. Okay. How about the infinite intersection? What do you get? Huh? Yeah. What? Sam? Who say? What did you say? Oh, okay. 1/real number. What's that? 1/infinity. Yeah. What's the other answer I heard? 0? 0. Set and then 0. Yeah. So for part 3, you also need to show this set inclusion thingy. So one is in the other. And then also from the line should be quite easier to see. So like -1 to 1, and then -half to half, and then -third to third, and then so on, and then keep going down. Okay, and then you following this pattern here, you string until 1 point, so you get 0. Okay, so 0 is in all the interval here, but maybe the other inclusion is harder. This one is a bit hard to show, but this is 0. Yeah, so you can see that this is let's say the interval, you see. So if you take intersection and interval, you still remain interval, but once you go into infinity, you are not an interval anymore. But union, it behaves well with the intervals. So you take finite union of interval, is still an interval, and then you take infinite, is still another interval. Like I can write this as another interval. So maybe I did something like this, which is the whole space. So yeah, so this is some properties of this real numbers here. This reflects some property on the real number, which we call the topology. Next, so we got the intersection, we got the union. Okay, so what is the next thing? So let's define this. So we call that two sets are disjoint. Disjoint if their intersection is empty. Okay, so why suddenly I introduced this definition here? Because we have this theorem here. So if you take the union of two sets and then you count them, you get the cardinality. And then it's actually the cardinality of A plus the cardinality of B minus their intersection. Okay. So for this, I think we should assume that AB otherwise infinite equals infinite, nothing like have to compare. So let's do finite one. So why the disjoint matters here? Because if the two sets are disjoint, then this number is 0. Okay, there's no intersection. So that means if you take the union of two sets, it's literally just adding up the two sets together. Okay, this is like the number, right? So if you add two numbers, 3 plus 5 goes to adding them. So it's like number. So if they are disjoint, it's just like adding number. But if they are the intersection is not empty, then when you count the union, right, you need to take away the middle one because this will count the intersection twice. So when you count A, you count this part. When you count B, you count this part. Right? So you take an extra intersection. But I won't prove this in class, but you can do it as an exercise. I think textbook also have it. Okay, next. Okay, next. You will get union, intersection, product. Now you can take the difference. You can take the difference of two sets. Okay, difference. A minus B divided by A minus B is the set containing elements in A, but not in B. Okay, sometimes we wrote A slash B. A slash B. So in the not form, what did you write? You write X such that X is in A, but X is not in B. For example, so let us take this running example. So 1, 3, 5 minus 1, 2, 3. What do you get? 5. So you get a set containing 5. Okay. So note that this difference is not commutative, meaning if I swap the order of these two sets here, you might get different set. What do you get if I get this? Okay, so far 2. Okay, so in A, but not in here. Okay, in here, but not in here. Meaning you take out all these numbers from here. Okay. So maybe I write by I write by here. Difference of A by B. Because N usually we say we can B and A and B is not much different. But in this case, the definition will be it's better for me to write. Okay. Okay, next. Next, what do we have? So next we have this universal set. Let us talk about this universal set. So that we can take another operation. So let's define this universal set here. So the universal set is the set. It's another set. So what's this set? So universe, right? Universe content of the galaxy. So containing all objects under consideration. So, okay, let's see what can this universal set do, right? So let U be the universal set. So you can take a complement of a set. Okay. Meaning if I take out the set, what is the thing that left behind? Okay, we wrote it as A bar. Complement. So this complement is an English meaning complement of A with respect. With respect. Okay. So sometimes we write AC, A complement, or you take away A. Okay. You take away A like just now also can like use session. Okay, so A bar is X in the universe and then because sometimes the set A may be hard to study. So instead of study the set itself, we study the complement of the set. We study what is beside. So maybe this person is very hard to understand. You cannot understand this person, right? So you go and understand all his or her friend. Okay. Complement of the set. Okay. So for example, let's take the universe as real. Okay. And then my set is the union of two open intervals. So what's the A complement is? What is the A complement? Huh? Zero? Zero. Huh? What? Zero? Why? Okay, let's see. So zero, okay, wait. So my U is like this, right? So real line. And then I take from -1 to 1. And then here is my point. And then here is my point. So I take away the arrow. So what do I left with? Ah, yeah. So it's a closed interval -1 to 1. So it's all the numbers here. Okay? Yeah. Okay. Okay, cool. Next. Oh, let me bring this thing up. Let me bring this up. Let me bring this up. Okay, let me bring this up here. Okay. Okay. So this is the Venn diagram. I think you're exposed to this before. So this Venn diagram here depicts two sets, okay, with non-trivial intersection. And then this two set lies inside a universe set. So let's try and figure out, ponder upon this figures here, and then try to write out what operation between these two sets will give this six pictures, okay? 6 shaded region here. Okay. Maybe try spend another 2 minutes and try write out what operation between A and B can give you the shaded region. Try. Something else. Okay. Let you work on it. Then I also need to work on something. The answer might be more than one, okay? Don't be. Might be more than one the answer. The more way you try, the more way you can see. Okay, let's see what's going on. Okay, so the first one, what do you have? Intersection of A and B. Any other answer? How about B intersection A? Same. How about 2? Anyone wrote B union A? B union A. Okay. How about 3? A complement. Okay. Any other way to write or not? Hmm? If you have, please shout out. 4? A minus B. Okay. A minus B. A minus B. Any other? No? About 4? 5, sorry. Okay, this one works. So any other answer? You also can take A slash B union B slash A. Right. Okay. Okay. How about 6? Okay. Oh, A union B is D. Actually, I also can write AC intersect BC. Yeah, so how I come across, yeah. So this one, you see, got remind you a bit of the De Morgan's. Yeah, you bring the C in and then this one turn. Okay. Okay, so yeah, so you can see this. Actually, we also have a similar set identities with these two operations here, the cap and cups. So we got the identities law and domination law. Remember the false are the true thing. Idempotence law. If you do twice, you get back yourself. And then this one is like the double negation law, right? Commutativity, associativity, distributivity, N or N. So become, and then De Morgan's law, just now we saw it. Assumption law, assumption law actually in set theory is more intuitive rather than the proposition one. If you take the intersection and then you take all of them, because the intersections still lie inside A, right? So if you union with A, you still get the larger one. And then if you take A union B, maybe become bigger or remain the same. But if intersection intersect with a smaller one, so you still get that. So the absorption law in the set theory is more intuitive. And then this complement law, remember the P and not P, and then P or not P is contradiction, or the tautology. It's tautology, then everything is contradiction and nothing. Okay, so remember the N and R from the last topic. Okay, so actually these are examples of another general algebra. So these are algebra. So because in algebra you need two operations. So now you all of these are propositional. So this one is propositional. Okay. And then this one is the set theory. So both of them have two operations, and then with this kind of similar identities, actually they are called Boolean algebra. So Boolean algebras we were learning in the past topic. Yeah. So it's a generalization of these two theories. Okay. Okay, next. So next we will try and prove this identity, one of it. As a tradition, we want to prove the De Morgan's law. So in at home, at your free times, you can prove these identities. Okay. Prove these identities at home, okay? And you are free, nothing to do with them. So these are the set equalities. So you need to show the two set equations, okay, for all these. So as a tradition, let's prove this De Morgan's law. So proof. So how to prove? Proof is proof this set inclusion is one of the technique you need to learn in this. So we need to show A union B is the subset of A of the set B, and A union B is a superset. Okay, so let's do the first one. To do the first one, we need to take an arbitrary x from the complement of A union B. And what it means then, it means this means that x is not in A union B, right? So because it's in the complement of A union B, so it's not in A union B. So if it's not in A union B, this implies what? X. It is not the case that X in A union B. Okay. So this one is just by definition. And then this one is just translating to what? To propositional logic. It's not the case that X is in A union B. And then the recall the definition of union. S is in A or S is in B. Recall the definition. And then now this whole sentence is a proposition already. It's not the case that S is in A or S is in B. By definition. So not and then not a disjunction. So we use a De Morgan's law. Not the case that and this is the De Morgan's law. So to differentiate the De Morgan's law in set theory and propositional logic, so I write De Morgan's law in the proposition. Okay, and then this implies what? This implies that X is not in A and X is not in B. Okay. So yeah, so this means that X is in A bar and X is in B bar, which implies that X is in A bar intersect B bar. This one is by definition. This one also by definition. Okay, so many by definition, later you confuse again. So this is the by definition of the intersection. Yeah, this one is the by definition of the complement. Okay, this one is just translating back to the set theory. This one by definition of the complement. Okay, so this one you show one way. Okay, the other way, you can do at home. The other set. Follow the similar set. Okay. Actually, basically, to tell you the truth, it's just going down to you can work it out. Yeah. If you are pro, next time when you are pro, then you just do this. Sure, proof. But yeah, step by step. Next, another way presented in your textbook, I think it's worth to mention it because this will remind you the truth table. But I prefer the set inclusion proof. So you must learn the set inclusion proof. Okay. So this one should remind you of the truth table, which you just have to quiz last week. Okay, in the set theory, we will write this as well. I will write a 1. Okay, 1 indicate the one here will indicate a specific element. Okay, let's say 1 1. 1 1 means they both this element exists in A and B. Okay. So 1 1 stay inside here. Okay. 1 0 means it is in A, but it's not in B. 1, 0 stay here. Okay, doesn't make sense if I don't label it. So here should be A, here should be B. And then 0, 1 is not in A, but in B. And then there's another possibility, 0, 0. So 0, 0 meaning lying outside. Okay. Because we want to prove these identities, right? We need to show it for arbitrary x. Okay. So we will see what's going on with this 1, 0 thingy. So take, if it is in A, so it's not in A bar, it's not in A bar. If it's not in A bar, it's in. If it is in B, then it's not in B bar. If it is not in B, it's in B bar, and then so on. Okay. So what is A union B? 1, 1, you get 1. Because if it A in B, so definitely in the union. 1, 0, you get 1 as well. Because in union, you take all the elements. So if in 0 in B, you still take it. If it's not in A and not in B, then it's not in the union. So you do the complement, you get 0, 0, 0, 1. How about A bar intersect B bar? So 0, 0, you get 0 because there's nothing inside there. So it's not in the intersection as well. So if it's not in not in A bar, yeah, and then in B bar, so what's the intersection? You get 0 because they're not the same here. 1, 0, you also get 0. 1, 1, you get 1. So they have the same table thing. 0, 0, 0, 1, 0, 0, 1. They lie in the same place. Okay. So this one, yeah. Okay, next, the last part of this set business is multi-set. Okay, last time we talked about this multi-set. So this multi-set here, now we allow similar element to occur multiple times. Okay, that's why we call it a multi-set. This should be important. I mean, useful. So multi-set is also unordered collection. So this unordered quite important because last time we talked about the Cartesian product, the order is important, but in the set it's okay. Where an element can occurs more than one. So for example, okay, this set 1, 1, 1, 2, 2, 3. Okay, this is a multi-set. If we regard this as a set, right, this will become a 1, 2, 3 set. But multi-set, we will take note of the multiplicities. Okay. So next, we need to tell you what is the multiplicity. So the number of times of an element appearing in the set is the multiplicities. So for example, in this previous set here, so what's the multiplicity of 1 in this set? What's the multiplicity? 3? Yeah, it's 3. Yes, correct. It's 3. How about the multiplicity of 2 in the set? 2. Yeah. about the multiplicity of 3. 1. 3, 2, 1, 1, 2, 3. Very good. Next. Okay, so maybe you can guess what's the definition of the cardinality of the multiset. What do you think? So it's just defined to be the sum. Okay, you sum all the multiplicity of all the elements. So for example, just now I give you this set here. So what's the cardinality of this set? 6. So it's 3 plus 2 plus 1 equals 6. Okay. Sum of the multiplicity. Good. Okay, next we have these. Okay, now actually I need to say something. So the subset, we can try define the subset for multiset. It should be the same. Same definition, similar definition to the set one. But union intersection difference sum may be a bit different. So if you take union of the multiset, again, you need to consider the maximum of the two. Okay, I'll show you later. So it's the maximum of X multiplicity in P and Q. Okay, for an element. Intersection, you need to take the minimum of the multiplicities of the element appearing in P and Q. The difference, you need to take the multiplicity of the element appearing in P minus the multiplicity of Q of an element appearing in Q. But of course, there will be a case that maybe it appear more in Q. In that case, then you will get negative. So you just take 0 in that case. So it's a maximum of the difference or 0. And then the sum should be the usual what you think of union. So just take sum of the multiplicity. Okay. So let's try this example here. Hey, where's the example? Okay, example. Let's try this example. Okay, so I'm not sure you are familiar with this maximum operation or not. Let me show you. So if you want to take a union, you take the maximum of the multiplicity that appearing in either one of them. So first of them, in A, the number 1 appear 4 times. In B, it appears 2 times. Right. And then how about 2? In the first one, it appears 2 times, and then B appears 4 times. And then in the third one, A it appears once, and then B appears twice. Okay, so you take the maximum one. So maximum of 4 and 2 is 4. So there's 4 ones here. And then maximum again 4. And then you get 2. Yep. 2, 3. Yep. Good. Very good. Next. So okay. So intersection, you will do the other one. You take the minimum of this number. And you take the minimum of the number. So minimum of 2, 4 is 2. Minimum of 4 is 2. Minimum of 1, 2 is 1. Okay, this is the intersection. Okay. How about A minus B? So the maximum of 4 minus 2 or 0. Yeah, very good. The maximum of maximum of 2 minus 4 or 0. Maximum of 1 minus 2. Oh yeah, right, correct. 1 minus 2 or 0. Okay, very good. Very good, very good. So maximum of 2 and 0 is 2. So it got 1, 1. Minus 2 minus 4 is minus 2 minus 2, 0, maximum is 0. No 2. So minus 1, 0, also no 2. Okay. How about A plus B? A plus B is, okay, it's a 4 plus 2 and then 2 plus 4. 1 plus 2. So we got 6, 1. And then okay, so let's see what's going on. So A union B, you just get 4 of these and then 4 of these, and 3 of these. Okay, and then A intercept B, you get 2, 2, 2. Okay. And then A minus B, what happened is you take away these 2. Okay. And then because you need to take away 4 of them, you only have 2, so 2 take away. So this one need to take away 3, you only got 1, so you take away. So you left with 1. A plus B, you just sum of them. Okay. So exercise you can do is find B minus A. Okay. And then you will see that B minus A and M minus B is different. Any question or not? Hey, I find myself getting very fast because I keep repeating the same lecture. For 3 groups, right? I repeat the same lecture. So each time I get faster and faster. So you stop me if you think that I'm too fast. Please stop me. They should put all of you into one class. Save time. No need to spread 3 hours doing the same thing. I need a very big one. Then we can do in the B1 or this B1, beside the library. B1. Very waste time. Do same thing, different hour. Any question or not? I think I stopped too much. Last class stopped at here. Next one we will do functions. Or you want to get into functions? Function matrix. Any question or not? You want okay, I give you choice. You want to go into function a little bit, or you want to do tutorial question, and then we'll also discuss quiz. Huh? What do you want? Huh? New content? Huh? What do you mean? Which progress? For the chapter progress? Last class we stopped at this place, and then I think the rest is function and matrix. So maybe I think function will take, let me see. maybe function will take a bit more than 1 hour, maybe 1.5 hours, and then matrix take about half hour, something like that. So within next week, we will finish this topic, and then the following week, the following week it's another quiz. So we start a new topic that week. Yeah. What do you think? You want to go into a new content? Yes or no? No. No. No, then we can. Okay, if no, then maybe we will spend longer time in discussing quiz. Maybe. So what to do now? Now it's 10:40. Okay, now 10:41. So we have a 10 minutes break, and then between the break, right? 10:51, come back, and then during the break, I want like row by row, you can come and collect your quiz. And then after you collect your quiz, you can take a photo to keep a record. And then after this class, you give me back the paper quiz. Okay. Okay, you can go into rest, and then the first row can come and find your quiz first. And then row by row, you can get back your quiz. Huh? What do you mean? Different. Oh, never mind, never mind. It's okay. As long I don't want congestion here. That's fine. That's fine. Or maybe.
This is 0 here. For what?
Oh, for what? Because you get negative here, but there's no negative element inside.
But there is 2, another 2.
What do you mean?
And 4 minus 2, there is another 2.
Yeah, this one 2, but this one is minus 2.
So 0 for what?
Oh, this is like, okay, for consistent, because every time you don't know whether you get a positive or negative.
Yeah.
So I have to add in the 0 to, if this number is negative, I take 0. If this number is positive, then I take the larger.
So
Just to be consistent.
oh,
Yeah, consistent. Yeah.
so I can put 2 here.
Cannot. If you put 2 here,
Yeah.
if this number come out to be 1, then you need to pick the 2, which is. You know what I mean? So 0 is like.
刚刚有一题哦，那个你画有6题的那个 set 那个第4题可不可以是这个？
我看一下，
可以不可以是这个？
不可以是这个，我要看一下哦。A intercept。A intercept B 的 Y intercept， 可以。
可以吗？
对，如果你要用 algebra 来 show 的话，应该也是可以的。如果你看这个是 AC union BC 啊 ，and then intersect with A 嘛，对不对？
哦，是。
And then 这个是 AC intersect with A union BC。OK， and then AC intersect。是 MD 啊，这是 MD。那 MD union with 这个应该就是这个自己哦，因为里面加东西进去，然后 BC intercept A 进去。
知道我写这个也是可以被接受啊。
可以，如果我叫你 show 的话，你就要写这个东西。
可以给我写。
对，就是用那个这个 algebra， 就这些。对。那你刚才不提出来？
我要写你已经到这里了。
不行，你可以直接拉我回去。对啊，直接举手就拉我回去。 因为没有人举手就过了，去过了，叫住我就会回去。对。
教很多人。My God，
慢慢来。
怎么找？
分一下，分一人找人。没找过这个，没找过。
但是这个是什么意思？
哎，
这个打分是什么意思？这个就是
因为反正怎样说呢，全部都除十嘛，所以我就算他的那个单数就好。
这是多少分？
这满分。
哦，
因为他满分100分嘛，100分，但是刚刚好我除的段嘛被10，所以除10哦。
哦，就是
要除100分。
我是满分是几个？
是哦，因为刚好除的段就不用再写
那么大了。
也，因为之前呀，对。Hello. The quiz. Ready for a quiz? Okay. The quiz is out of 10 because it's divisible by 10, so yeah. Instead of writing 50 every time, just write 5.
So because of 2 page, each for 5.
Yeah. Mm.
10分里面拿6分，没事。
对。
以为是6分。
Okay. Yep. Last slide.
The one that with min max.
This one.
Yep.
Yep.
Again, I don't really like pay attention.
Yeah.
Why should we use max and when should we use min?
So max is during the union, min is during the intersection.
So it is max. That's
Wait. Okay. There are few. Okay. So definition is like this, but whether you're asking why define this is the question. So the definition is like that. So here's the definition. So the multiplicity of the element in the union is the maximum of the multiplicity in different sets. And then for intersection is you take the minimum. Yeah, this is the definition. But why we define this is yeah. Are you new here? Are you just come or last week you're here? Oh, okay. Oh, you're here. Okay. Because it seems like I just see you this week.
He's been here for the whole time.
Oh, whole time, okay. Because like not active, like not too lazy. Okay. Yeah. So yeah. So this is the definition. But of course, you can ask why we define it. Yeah. So why not intersection is the maximum? Why not the? Yeah. Why not? Yeah. You can think about it. There's a. I think there's a. Yeah. There's a reason. You can think about it. There's a reason.
I borrow your laptop or I want to see the laptop.
王栋他感染了新冠，请回二十。
谁？ 你的同学，
对，
那他那个发邮件给我了，
是有这样发给哪个老师吗？我们的
对，我跟他说要发给，对，
他是不用你申请，要发给我，
啊，可以，等一下发给我，可以，你可以拍照，
跟他说一声让他发邮件。
对，叫他发邮件给我，因为我要记录。
然后老师想问一下，这些证明题是直接可以用数字 table 证明的？
哪一个证明题？啊，对，聊天环那个，
但是就是课件上那个 A 和 B 的纸面的 X 上面画个横线，不然那个图出来，它不也很正经吗？那个可以直接用数字 table 证明。
我考试应该会要求要用 Seng，如果我要啊，因为对，因为我比较喜欢那个 Seng，
就这样。
对。Okay, I pass down the attendance. If your friend got COVID or what, cannot come or sick, you can help them to take picture and then send them, okay? Okay, and then this quiz I just wrote out of 10 because it's divisible by 10, so just out of 10 is easier. And then for just now, right? Just now, someone got different answer for this Venn diagram here, part 4. Okay. You also can take A intersect B, and then take the complement. So A intersect B, and then take the complement, and then intersect A. Okay. So you can use the algebra here, the identities here, to show that it's actually A minus B. Okay, you also can do this. It's okay. So the equal sign here is the set equalities. Very good. Similarly, you can use different way to get this picture. Yeah. Very good. Yeah, this one. What else? Oh, one person asked me why put 0 here. Cannot put 1, 2, 3, 4, 5, 6. Why not put those numbers? So I think it's good that you got this variation, because this will question why we define like this. So let's say if you put 2 here, okay, then if this number come out to be 1, then the maximum is 2, which is wrong then. Okay. So 0 is just how to say, safety pins. So if you get a negative here, so you just put it as a 0. But if you get any other positive number, then you should take those positive numbers. Okay, this is just a way to prevent negative. Okay, let us try and discuss the quiz. So the quiz here, so what I want you to learn from this quiz is how to write a proposition. So I asked a question in the question, ask a question. So it is a question we already did in the class. Why is it not a proposition? Because it's a question. Or you can answer it has no true values, it's not true or false. You cannot answer true or false. But you cannot say, someone say because it is not a statement. But I define proposition and statement as the same thing. So if you answer like that, it's not answering the question. Okay. It's like repeating the answer. And then second, I think the most common one will be KFC drumstick is better than Mamas. So as long as it's a proposition, I will accept. So what is question 1.3 asking? When is the proposition you just make false? So if the proposition you met is false, that means not P is true. So actually this question is asking about negation of your proposition. Okay, so this question is asking for what is the negation of your proposition. Okay, next one. Next one, I give you a real life example. So I want you to realize that how to break the compound proposition into propositions, and then what is the relation between the proposition, whether it's a conditional or disjunction or conjunction. Okay, and then I gave another compound proposition so that you will notice that it is a contrapositive actually. Okay. So, and then in this question, I ask you to prove that a segment is logically equivalent to the contrapositive. And then to show this, you have two ways, either showing that they have the same true value, or the biconditional segment is a tautology. There's two ways you can show it. Okay. So let's see some answer from your classmate. So I'm not sure it's fortunate or unfortunate, but the logic here is true. Actually, the question is true even if you don't know about what is mama and capsule. And also even you don't know what is better is. You still can answer a question. Okay. So this is like, this logic is what used to build the robot. So that's why people say the robot has no feeling. Right? So yeah, someone said here, to be honest, in my homeland where I was born, there's no Indian Muslim there. In conclusion, no, there's not. Okay. Yeah, okay. Another thing is someone changed my adjective. They changed to is it this one? Let me, not this one. This one is something weird. Let me see this one. Yeah, they changed my adjective to delicious, cheaper, yummy, bigger. Maybe better is different for you. You think bigger is the better, but unless they are equivalent, then you can change. See the next one. I think this one pretty good nowadays. Some of them write the P or not P. P or not P is the tautology, so it's never false. It's never false. Tautology is never false. And then some write contradiction. Contradiction is always false. Yeah, always false. And this guy write that it's better if it is in the weekend. Then yeah, I think this one quite good. This one this guy quantify the better, so he defined the greater, less than, equal. And then this person here, nice question, nice proposition. So right, if you prefer Indian cuisine, then mama is better than KFC drumstick. Yeah, I think this is quite reasonable. So what's the negation? When you prefer Indian cuisine, but KFC drumstick is better than mama's. Yeah. Okay. Quite good. And then this one, this guy also very good. I think this boss like the boss will like you a lot, because he provide the negation and then also suggests how to test it. And then this person, I think, is from the other class. He said if KFC drumstick is better than mama, then Seng will go for KFC drumstick. Yeah, in fact, this is the motivation. I mean, this is the where I get this question from. Like the first day I reached here, so the person bring me to the mama, and then I try to translate. I think not that nice, but it's very expensive. So that's why I come up with this question here. Did you all know mama or not? Including the international students. Have you tried the mama here yet? Actually, mama also new for me. Although I was from Malaysia, I was from Sarawak. Sarawak don't have much mama. We have less Indian, and then of course less Indian Muslim. Okay. Any question on these quizzes? If you have any problem with your quiz, you can come find me. You can email me, and then we'll figure it out. Okay. If not, we can start on this general question and discuss with your friend, and then work it out. And then we'll do it maybe 11:30 or 20. In the other class, I found out that some of the students use Chinese text. I don't know about you, but if you are using Chinese text, make sure you also read the English text because the exam will be totally in English. There's no Chinese text. So make sure you understand the English question.
Yeah, okay, let me answer that. Let me answer that. 哎，这边，等一下，等一下，hello, hello, 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 testing. Yeah, I think there's a phrase that I didn't introduce. You confused. So I introduced this. Okay. So set builder notation. So I think they refer to something like this, I think. Okay. So if like this listing one, they call it a roster method. Okay. Set builder notation. Okay. Not very specific to the region that they can define. I mean, 我不知道你现在这个在 R 的话是怎么你这边要那个 或者说 it's too something。如果你不是，我这边有好几个，就是如果可以 mix like that。他自己的人我要找的那个位置，也就他我的世界，我的世界跟我们。我接触过来这边，我是直接3 X 我这边是没有关系的。你懂没？这句话其实也不太完全，这个应该是这种。因为如果我把 X 定在 V 里面，在这里面不止分出，我们有3点。Actually 就是1到5个里面的开始到像这个的话，我主要是第一个里面2到5样，因为它不是很多，它是有上面，对对，那个佛倒是没的，这样理解，我不的话，那边不，那里发现，yeah, think about it. Yeah, try think about it. Yeah, try think about it and then see how you speak to it's yeah,你看这有没有规定的那些是呀？
就是我觉得他这个写的不对啊，是合理。现在这个和这个都是
通常如果我们看成 set 的话，这个就可以简略了几个东西。如果看 multi-set 这两个就是两个。
而且现在和现在不一样。
但是这个是 set 版，所以呢，
我觉得这个不很像。
对，就是
可以多一点，但是它就是等于这个，就等于我们就等于。如果在 set 里面，如果那个 M 那我们就会把它去掉。
为什么里面有个 set， 里面只有一个 M 字，那个是在同一个 set 里面才会出现。他每个 set 都有看。
这个我跟现在我是个当时干的，但是我跟现在的是怎么样的？
对，你可以讲一样的。对，不能讲这样子嘛。哦，如果讲一样，对，如果讲一样，那就把一分做一样的。这个是放在。没有。这个但是可以是大的，重点就是这个对不对？所以讲啊。对哦，所以我就说这个可以，如果是把它看成 set， 把它理解。
所以是没有错。
就是把什么事情啊？对。
你这么写成好像要吃吗？好吃，就是牙膏的。
就
好的，不是错的。
我觉得可以换，跟那个有一个体感的。哎，我说那个地方跟什么？这方面2.2。
2.2要过第几题？没事，你不要也是这个好事。我连定了也没有怎么去。
你们全部都写中文，哪里看错？
啊
老师的有一题，他预测 paradox 我看不懂，
，Russell Brother，哦，等一下我解释。Yeah，OK，
全看不懂他讲什么。
OK，好。Hello. Okay, let's come back. Okay, let's come back. Let's discuss. So in the 2.1.2, so just now we mentioned about the roster method. And this one, okay, finally I found the name for it. Actually, I don't know the name. Okay, it's a set builder notation. I write a predicate through set, so it's a set builder notation. So set builder notation is like maybe sometimes the things you consider they form a pattern, so you can describe them easier. So usually you put where's the domain in this column here. If you change, remember just now I told you if you change the domain, this set might change. So make sure you explain where the domain is. And then for the B, it's the integer, and then you fix the range for them. Okay, make sure here is a predicate. Okay, this is actually a sentence, which is x is in between 3 and -3. And then MNOP, I wrote here is the letter of the monopoly asset L and Y. Anyone have a different description of the set that you want to share? Anyone have different? Three of these. If you have any different one, no.
Describe C.
X is in the domain, so X is in the, okay, maybe we also call the alphabet set. Okay, call E English alphabet, so it's in E, and then okay, and then what's the condition?
We got X and the range is from M.
The range is from M to P. I think this one quite common because I see the other also write it. But the problem with this, okay, I'll tell you what's the problem. So the problem with this, do you have an order on the alphabet? Yeah, so do you have order? if you have an order like A, B, C, D, E, F, G, H, then you can say like this. Okay, if you an order of this order on the alphabet, then you can do this. Okay. One way to give this order, right, you can form a map between this A, B, C with 1, 2, 3. Yeah, you can do this. Dictionary. Yeah, if we touch on function, then you will see that this is actually a function. So you define a function. And same thing.
So this one.
Oh, this notation is a bit weird.
But somehow shows the order.
Still don't. Okay. So unless you got order, you can do this. This. Okay. Any other different question? Answer to these 3 questions here. Any other different one? You think it's a different one? They want to change, or you want to check? Okay. Later we will come back again. So this question, right? For 1.2.12, I think there's one key. There's one key concept you need to unstuck or stuck. Unstuck. Not sure you're stuck or not. But the key question is here. So is the empty set equal to the set of empty set? Okay. So, okay, no. Why no? So suppose we want to show true, right? If we want to show true, that means we need to show 2 set inclusion. Okay. Okay, we need to show these 2 set inclusion. Okay. First one, empty set is a subset of the set of empty set. This is correct because we proved that every set contain empty set as a subset, and also it's a. How about this one? Why false? Okay, so for this, I have to show that for every x in the right hand side, the set of the right hand side, every 7, and then x is in the phi. Okay, right. In particular, I can take x equal to phi, right? Because this is the element in the set, and then need to show that the p is in phi. Okay, and then this sentence is false. Okay, don't want it's false because p doesn't contain any element. Okay. So empty set is not an element of empty set. Okay. After you doing this question should be a bit clearer. And then this one, maybe some of you were confused with this set here. So this set is like repeating the element here. So if it is a set, we usually just remove the repeating one. We just look at the distinct element. If it is multi-set, then these 2 will be counted. So if they don't mention multi-set, then usually it's just a set. Okay. So this one purposely confuse you because actually if I write out this, then it should be clear already. This is x as a subset of x. Yeah. Okay. Yeah. For this proper and non-proper, right, you also have to take note. A lot of you also ask me about the difference between proper and non-proper. So this one is proper. Okay. So subset. Subset. So subset only have one condition. Proper subset have two conditions. You need to show. Okay. That means you need to show something in B which is not in A. Okay. So so if you remember the predicate logic, proper subset implies subset. Okay. Because if you have P and Q, you can deduce P. But if you have P, you cannot deduce P and Q. In other words, proper subset is a stronger concept than subset. Okay. This is the relation between the subset. Okay, proper subset, subset. Yeah, so that's mean in EFG here, you need to show that there's something in the right hand side that's not in the left hand side. Okay. For example, this guy here is not in the left hand side, and this guy here is not in the left hand side, and then oh, G is false, is it? G, what's the question? Is it G false? G true? G false. If it is a proper subset, then it's false. Hmm? A is what? A correct. A. This one is false because you cannot find an element in here that is not in the left hand side. Yeah.
So one more time again.
Yeah, the concept. So G, the right hand side or the left hand side, right hand side. So the left hand side is a subset of the right hand side, but it's not a proper subset because you can't find an element in the right hand side that is in the left hand side. That's not in the left hand side. What is it? Ah,
Yeah. That's all. So I need to have two sets of data. Left side.
instead of left side. No. No. So you need to find something in here which is not in here. You need to find something in. You need to find something in the right hand side which is not in the left hand side. But you can't find it. But the right hand side, yeah. And you cannot say larger. Okay, larger, yeah. Can. Huh? What? But larger. How to say? Wait, no. Larger. If it is infinite, right? Larger doesn't mean anything. But you can think of it larger. But when you go to infinite, huh? No. I mean, when it is infinite, it's hard to tell which one is larger or small. Huh?
Therefore, E is also false.
For E is also false. No, because for E, right, this element here is not in here. Yeah. 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 Okay. Okay or not?
I think I got it.
Okay. Okay, 2.1.22. So the cardinality of empty set is 0. Okay. The cardinality of the set of empty set is 1. The cardinality of set containing empty set and the set of empty set is 2. Then this one is 3. See, this one is what I introduced in the class, right? Cannot exceed. See, you take the cardinality, then they reduce the to 0, 1, 2, 3. Okay, so actually when we like, remember I defined this as 0, define this as 1, define this as 2, define this as 3. Right? The successor. Yeah. So how this number comes about, right? Is like the ancient time, the shepherd, they want to compare their sheep with different shepherds. So I got a herd of sheep, you got a herd of sheep. So who got more? So they come up with this number. So this number is an invariant of the sheep. Okay, next 2.1.24. Can you conclude that A equals to B if A and B are two set with the same power set? Yes, why? What the answer? So if you take the union of the power set, right, it's just X because you consider the set of all subset. Okay, it's the set of all subset. That means all of them are subset of your original set. Yeah.
I think the union will become
Mm.
set of A and B.
Okay, so let me write down. So if you take, so let me think how to write. So the union of X, union of let me think how to write out. Union of power set. How should I write? Union of X such that X is in the power set of S. Okay, is S. Okay. So you take the union of all the set inside the power set. Okay, it's actually the X. You get back your X. Okay. Maybe this is a good exercise you can try to prove this. Huh? How to prove? How to prove? Just use the definition of power set union. Okay. Or how to prove by constant positive. So this sentence is like if A and B are two sets with the same power set, then A equal to B. Okay, so constant positive is suppose A is not equal to B, then they are not two. They are two sets with different power set. Right? It's easier because if they are not equal, that means they have different elements. So if they have different elements, then you can produce different subset. Right. Mm. Any question from the back? From the back, no. Okay, 2.1.26. I think this one also a bit hard for me. So you want to decide whether a collection of set is a power set of some other set or not. So A is no, because power set must have at least the whole set and the empty set. So it can't be empty set. And then B is a power set of A. C is not a power set because you notice that you still can produce another non-trivial subset. Okay. So another way to check is actually this set only have 3 numbers, which is not a power of 2. Usually it's a power of 2, number of power set. And then D, you can figure out this is the power set of some set. Okay. 2.1.50. This one, Russell paradox. This one very famous one. So suppose X is a set such that the condition is the element is not belong to itself. Okay. Yeah, very weird condition here. So if you suppose that S is in there, then if X is in there, it follows this predicate, right? So X is not an element of itself, so it contradicts with itself. If X is not in there, then because it satisfies this predicate, X is in the set. Okay. So by definition, so contradict again because you assume not in and then you prove that it's in. So what is the moral of this paradox? The paradox here, the moral of the story is you need to specify the domain here. You cannot just simply put some X in. Okay. Once you specify the domain, you restrict your element and then it should work. Okay. So you need to specify the So you need to specify the domain of that. Otherwise, you can jump into some paradox. Yeah. Understand which one? This one, 50. Well, what's the question asking? So yeah, so this so the question is whether this X exists or not. You can define this kind of set on, right? And then what's this set here? This set here is set of all set such that the set is not an element of itself. Does this set exist? Yeah, the question is this. Yeah, no, because suppose I take this X itself, I check whether it is in there or not. I get that it's not in there. No contradiction. Suppose it is not in there, because there are two conditions. If you take a set, whether it's in there or not in there. If in there, a contradiction. If not in there, still a contradiction. So there's nothing in there. So you can't define such thing. So the moral is like you need to specify this domain. So you cannot simply just take everything. Huh? Can't just simply say, can't just simply put anything here. So you need to like specify, like if you don't specify, then I simply take something that doesn't work. Okay. Okay. Negative X.
Yeah, for first one.
This one.
Define like negative X is not enough, right? Somehow we go.
No. What does a negative set mean? What's a negative set? This is not a number anymore. This is just a set. Any set. Just a set, not a number. These are not number. These are a set. Yeah. Is there a domain that make it work? Maybe. I don't know. Maybe. I don't know. Or the predicate is, I don't know. Yeah. Okay. Yeah, not defined one. And then 2.2.4 is a standard question. And then 2.2.12 is what I want you to learn, how to show set equalities using the set inclusion. This one you must know. how to show. And then 2.2.16 is also exercise to show the set inclusion. And then 2.2.54 is similar example to the cluster. If you don't have any question, then we can dismiss. If not, you can ask.
A is the power set of A. Yeah.
A is the power set of A. A contained in the power set of A.
Yeah. And the P is the